It doesn't go over. But this is not always.
All right, guys. Good morning, everyone. I hope that by now you're familiar with wellbore stability and that you are preparing for the exam and for the homework first and for the exam later. Remember, the exam is going to be on Friday afternoon. So, talking about the exam, to remember that the exam is going to be mostly based on fault analysis and on wellbore stability. Those are the two topics. I'm not going to take any other problem outside those two. But remember that in order to solve those, you need to know how to compute stresses at depth. That's probably the most important thing that you should know in order to get your problem right from the very beginning. Compute stress at depth, review stress faulting regimes, and also check how to compute pore pressure whenever you have overpressure and it's not hydrostatic. Very important too, practice on how to compute equivalent weights in terms of gradients, in terms of pounds per gallon, computations of weights in equivalent circulation density. Okay, so far what we have seen is how to calculate bounds for wellbore stability depending on either considering a lower bound that could be most times caused by shear failure or some other times, but also not going below the value of pore pressure, and an upper bound, which would be the higher pressure at which you can get in the wellbore. And usually that upper bound is related to tensile fractures, and sometimes most what is more dramatical, it would be to have a very large tensile fracture that could lead to a hydraulic fracture, that could lead to lost circulation and loss of drilling mud as you are drilling. And usually for that, that's a higher pressure, usually not always the case, but it's a higher pressure than this one, and the value between those is what we call the mud window. So we have seen how to do these calculations, and we have seen how to compute these stresses. By the way, I received questions about what you should plot in problem number 1 of the homework. You could either do a surface plot similar to the one that I have in the notes. So by the way, guys, I have already uploaded a new version of the wellbore stability chapter, so it's already here. If we go to wellbore solutions, we have something like that. But you see, that would be a surface plot as a function of x and y, or as a function of r and theta. But something else you could do to make it a little bit easier and to make the comparison easier too could be to plot this sigma r and sigma theta theta. You just choose one theta, say theta equal to 0, and you plot sigma r and sigma theta theta as a function of r, and you choose theta equal to pi over 2, and you also can plot those two as a function of r. Yes, Ms. Aldawi. Yes.
Can you explain again how theta is measured, like starting from where, going clockwise or counterclockwise?
Theta is always measured from the direction of the maximum stress in the plane perpendicular to the wellbore. So, for example, this is not the best example, but it would be this one. Whenever you have a stress direction which is higher in one direction, you will measure it from that direction. That's from where you always measure theta. So, for example, now let me go.
Counterclockwise?
It's the same. It's the same, but I will go counterclockwise. So let's see. Here we have another example, right? Here, say this is SH max, and this SH mean, always theta is measured from the direction of SH max. So, well, with these equations, now we have been able to compute these two very important quantities, which are one, the breakdown pressure, which depends on tensile strength, and two, the pressure for obtaining shear, either a very tiny shear at the top of the wellbore in this case, or a larger shear region if we allow for a breakout. But basically those two equations are for shear failure in the wellbore. That will give you your lower bound. You put those two together, and together with some other considerations, and you can get to what we have called a mud window, and those will help you define a lower bound and an upper bound for setting what is the density that you need to drill a wellbore and to design where to put the casing. As you might expect, the lower the number of casings that you use, the better that's going to be, and it's going to make the drilling more efficient and also cheaper. So understanding this window is very important. Enlarging that window is very important. I don't know if you guys have taken a class from Dr. Gray, but Dr. Gray has worked almost all his life on trying to understand this a little bit better, and he has a research project which is called wider windows, because the objective of this is wellbore stability analysis. It's to enlarge these windows to improve drilling. So basically those are the fundamentals of drilling, and in the drilling classes you will see a lot more of technical contents about drilling fluids, about how to manage this pressure, sometimes with other controls other than just the weight of the mud, and how to enlarge these windows as well. What we're going to do next is to apply all these concepts that are exactly the same for what we have already seen, but we're going to apply these now to deviated wellbores. As you know, deviated wellbores now are a huge part of the activity, especially for unconventionals, and for reaching to regions where before it was either difficult or you needed more wellbores. I recently heard about someone saying that it was a talk about water flooding, that somebody is saying that one horizontal wellbore is as good as 8 vertical wellbores in terms of sweeping efficiency. And understanding how to drill these horizontal wellbores now, it's becoming very, very important. So let's start with deviated wellbores. You will see that the concepts are the same, and actually we won't spend a lot of time in this, because as soon as I tell you how to approach these problems, you will see it's very easy. So in order to get to this problem, let's consider a place where you drill a horizontal wellbore, and sometimes one of the benefits of horizontal wellbores is that you can drill from a drilling pad at a given location, but you can reach out miles away with a much lower surface use than if you were to use vertical wellbores. So let's say that you drill this horizontal wellbore that it starts vertical, and at some point it deviates in that direction. And let's also say that this is an example with normal faulting. So SV is higher than SH max and higher than SH mean.